Hi and welcome to Unit 1, Topic 1, Video 2, where we're going to look at some examples of applying probability and counting principles, just basic ones, to some pretty simple questions. But again, I hope that it will give you some deeper understanding of the multiplicative, additive principles, and maybe tree diagrams if we need it. So let's have a look through them. Question 1. Trang has 5 skirts, 3 tops, and 4 pairs of shoes. How many different outfits can she assemble using these clothes? So this is the multiplicative principle in action. She will pick a skirt and a top. Now, they're not combined. We would wear one of each. And shoes. We would also wear one of each. Of course, if we had skirts or shorts, we might add that together because it's unlikely she's going to wear a pair of shorts and a skirt. So that would be then that option. So we're talking 3 options. We've got leg wear, we've got a top, and then we've got footwear. And we multiply those 3 options. There are 5 options for skirts, 3 options for tops, and 4 options for shoes. Multiply them along, and that gives us a total of 60 possible outcomes. So the answer here is, of course, 60. Question 2. There are 3 flights, or 3 different flights from Melbourne to Sydney, and 2 different train rides. How many paths are there from Melbourne to Sydney? Okay, so 3 different flights from Melbourne to Sydney and 2 different train rides. Well, this looks very simple to me, like an additive principle. AP, so here's our Melbourne, here's our Sydney. We can either get a plane, there's 3 of them, or we can get a train. And there's 2 of them, and that gives us a total of 5 possible ways of getting from Melbourne to Sydney. Now, hopefully this is a really trivial question. You read that and you think, am I trying to be tricked here? But when you take time, I want you to see that that is an additive principle style question. There are 3 different flights from Melbourne to Sydney. This is question 3 now. And then 2 connecting flights from Sydney to Auckland. There's also 1 direct flight from Melbourne to Auckland. How many paths are there from Melbourne to Auckland? So this is now a combination. This is additive principle, multiplicative principle. Let's draw this as a map. Melbourne to Sydney to Auckland. So from Melbourne to Sydney, there are 3 flights. 1, 2, 3. And from Sydney to Auckland, there are 2 flights. And these are connecting flights. Or we can fly directly from Melbourne to Auckland. So how many ways are there of doing this? Well, we have 3 ways of going from Melbourne to Sydney and then 2 connecting flights, which means that there are 6 different possible ways of going from Melbourne to Auckland via Sydney. And then, of course, there's that 1 additional way, just going Melbourne directly to Auckland. So we have the multiplicative principle at work to do the 3 times 2 to work out the total number of flights via Sydney, and then the additive principle to work out the additional flight on a different route. And that gives us a total of 7. So question 4. How many different 3-digit numbers can you form using the digits 1, 2, and 3 if the digits can A, be used as many times as you like? So in this case, it is the multiplicative principle, and we are multiplying because we have 3 options for the first number, 3 options for the second number because we can, of course, use the number again, and 3 options for the third number. So there are 27 different 3-digit numbers formed with the numbers 1, 2, and 3 available. Now this includes 123, but it also includes 111 or 223, where there's repeats of numbers. On the other hand, we have the multiplicative principle for part B, at most once. So in this case, there are 3 possible numbers to choose for the first digit, only 2 available for the second digit because 1 is already taken. We don't know what it is, but there's definitely only 2 left. And then there's only 1 remaining number. And so there's 6 ways of doing it, where each number is used once only, and there's no repeats, which of course means that there are 21 numbers made up of the digits 1, 2, and 3, where repeats do exist. So that might be a question you might get as well. Okay, question 5. How many different 3-digit numbers can you form using the digits 0, 1, 2, 3 if digits can be used as many times as you like, and again, at most once? So our A in this case, as many times as you like, we have to be a little bit careful. We're still dealing with the multiplicative principle, but in this case, we're going to make the assumption, as it's a 3-digit number, that we have digit 1, 2, and 3, but digit 1 cannot be a 0, otherwise it's technically a 2-digit number. So there are 3 options for digit 1, and then there are 4 options for digit 2, and 4 options for digit 3. And so 3 times 4 is 12, times 4 is 48. That includes 103, but it doesn't include 0, 1, 2, because we can't have a 0 at the front. For B, we get the same thing, the multiplicative principle here. But this time, we've got to calculate the number of ways we can do it at most once. But we've got a little bit of a problem now, and that we've got to deal with the 0 in a little bit more of a technical fashion. Because there are, of course, 3 ways of picking the first number. We remove one of the numbers, 0, 1, 2, 3, and we get 3 ways of picking the second number, and then we remove a digit and we get 2 ways of picking the third one. And so that gives us 18 possible ways. When I say we have to be careful, this becomes the hinge point. And we're lucky in this case. The natural order is to start with the first digit. But there is more constraints on that first digit. So if you had a problem that said you had to finish with an odd, well then I would consider starting by looking at the third digit and how many options there are for the third digit and working backwards rather than forwards. Or, as we'll see in later videos, breaking it into case-by-case situations. So there we have question 5. Question 6. How many ways can you arrange the letters in the word plus if the letters can be used at as many times as you like and at most once? So it's quite similar to question 5 and still a multiplicative principle question. So we use MP and we have 4 times 4 times 4 times 4. Now, it's a bit of an unusual question in that it doesn't say what length word we're creating. And when you can use the letters as many times as you like, of course, it could be a 100-letter word or 1,000. So we need to come up with a little bit of an assumption based on the question here. And the assumption we're going to use is that we're dealing with a 4-letter word. And that gives us 4 to the power of 4, which is 256. And then part B, how many ways can you arrange them if each letter is used at most once? And so we get the same idea. 4 times 3 times 2 times 1. So we choose the letter P, L, U, or S, and then we remove whichever letter got chosen first, leaving us with 3 remaining letters to choose for the second letter, and so on and so forth. And then question 7. And this one's a little bit different, so we have to be a bit careful with how we do things. How many 3-digit numbers can you form using the digits 1, 2, 3, 4, 5 if the digits must occur in increasing order? So we're dealing with 3-digit numbers and the digits must occur in increasing order. So if I try and do this one with the multiplicative principle, hopefully you'll see it breaks down quite quickly. The first one, well, there's 3 options here. 0, 1, 2 are the options that have to be chosen. Can't be 4, otherwise the digits won't occur in increasing order. Because 4 is gone, 5 is the only one left to fill 2 spaces. So we've got 3 options for that one. And then we've got a problem. Because if 1 is chosen, well, now it could be 2, 3, 4 as the second digit. But if 2 is chosen, it can only be 3, 4. And if 3 is chosen, it can only be 4. So this could be 3, 2, or 1. And this is where I'm going to fling back to a pretty basic looking tree diagram. I'll need lots of room for the first instance, but then things will come out quite easy in the second and third. So if I pick a 1 first, well then my second digit could be a 2, 3, or 4. If I pick a 2 first, my second digit could be a 3 or a 4. And if I pick a 3 first, my second digit can only be a 4. Now if my second digit is 4, then I can only have a 5 next to keep the increasing order. If my second digit is 3, well then I can have a 4 or a 5 next. And if my second digit is 2, well then I can have a 3, 4, or 5 next. And so of course that gives me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible outcomes. So the answer to A is 10, but we had to recognise that the constraints in this case have led us towards either a tree diagram, and it's a pretty small question, so tree diagram's good, or a case-by-case situation. So now let's have a look at question B. So in question B, I'm going to use a tree diagram again because that's what the focus of this exercise is. How many three-digit numbers can be formed from the numbers 1, 2, 3, 4, 5 if adjacent digits differ by 2? So what I'm going to do in this one is I'm going to be really thoughtful about my choices of the central digit. It seems to me like that's the most important one. So I'll show you a tree diagram in a moment, but we can do this logically. Now, firstly, let's assume that you cannot choose any numbers more than once, because that's what we've done in A. So if we do that, well, let's look at my middle digit here. Really, if that was a 2, then this would be a 4, but then this would have to be a 0. If that's a 1, it doesn't really work. The only thing this can be is a 3, and this is a 1 and a 5, or a 3, and this is a 5 and a 1. So there are two options in that line of thought. Of course, if repeated digits are allowed, well, then we have more options. And that is, let's start with 1. Well, then we could have 3 and 3. That works. But there's no other options for 1. 2, 4, and 4. That works, but there's no other options for 2. 3 we know can be 1 and 1, or 3 can be 1 and 5, or 3 can be 5 and 1, or 3 can be 5 and 5, and then things get a bit boring again. 4 can only be 2 and 2, 5 can only be 3 and 3. And so there are 8 ways, depending on which way we look at it. The tree diagram for the first option is quite simple, and I think that's really the correct answer given the context of the question. The tree diagram for the second option is a little bit more interesting, and I'll draw it for you now. Okay, so here's my tree diagram. I can have any number up first, and I'm doing it in that first number order, but I could do it starting at the central number if I wanted to. 1 has to be followed by 3 to get that rule in place. The adjacent numbers are separated by 2, and 3 can be followed by 1 or 5. 2 has to be followed by 2 or 4, which has to be followed by 2. 3 can be followed by 1 and then 3 again, or 5 and then 3 again. 4 can be followed by 2 and then 4 again. 5 can be followed by 3, which can then be followed by 1 or back to 5. And they are all of our options there. And so this is a visual way of representing these possible outcomes and a good way to think through the problem, especially initially. So there's our questions on the revision of probability principles we need, particularly tree diagrams and that counting concepts, but also questions on just general counting techniques leading toward permutations and combinations. All the best.